Okay, so this is an example of the horn antenna. As you can see that we have a different types of horn antenna here. Okay, so this is a horn antenna. So this is one of the different type of, I think the very simple horn antenna is based on the waveguide. Now you see. So this is your waveguide. Now you see. And is there anybody knows how to want to determine the cutoff frequency of the waveguide? Okay, so this is also horn antenna. So this is a corrugated horn. This is also a horn antenna. So you can see that this is a broadband horn antenna, horn antenna. All this is what we call the horn antenna. Okay, so the most important thing for the horn antenna is the waveguide dimensions. So this, you learned about the waveguide before. So waveguide actually is a hollow tubes where the electromagnetic can propagate inside the waveguide based on the modes here. So there usually is by reflections throughout the wall. Okay, so what we can see here for the waveguide, how you want to determine the cutoff frequency? Is there anybody knows how you want to determine the cutoff frequency of the waveguide here? Okay, if you have the dimension like this, A and B, so this is the waveguide. Okay, so how you want to determine the cutoff frequency here? FC here. Is anybody knows? But anyway, okay. So if you have the aperture like this, A and B here. So this is the aperture of the waveguide. Very simple. So if you want to determine what is the cutoff frequency or the frequency that can propagate inside the waveguide, so we can use a general equation for the waveguide. FC is to C over 2 square root of your M over A squared plus N over B squared. So this is a general equation for the cutoff frequency of the waveguide. C is your velocity of light in a free space, 3 times 10 to the power of 8 meter per second. Okay, divided by 2. And then if you have like the dielectrics inside the waveguide, so you have to divide by square root of your epsilon r. So we assume that in the waveguide, in this waveguide, is only the free space. Okay, so from here, M actually and N is the modes number, because in the waveguide we have a lot of different modes. So because in the waveguide, what you have learned before, you have in terms of a TE and TM. So this is your M and N. M and N is the modes number. Okay, so it means that the modes could be infinite. You can have TE, TM11, TM21, TM31, and so on, or TE10, TE01, TE11, TE21, and so on. Okay, so usually if you want to determine the cutoff frequency for this particular waveguide, rectangular, we consider that our dominant modes. Dominant modes, it's what we call is a TE10 here. So this is a TE10 is the dominant modes. What is it meant by the definition of the dominant modes here? Eng Zong Ying, what is the definitions of the dominant modes here for the waveguide?
Sorry, sir, I'm not really sure.
You are not very sure. So what do you sure? Is there anybody can give me the answer? Okay, so the dominant mode is basically is the lowest mode. The lowest mode that the wave can propagate. Okay, so for the waveguide, here we see for the rectangular waveguide, the dominant mode is TE10. What does it mean by the TE10? TE10 is the lowest mode. Okay, the lowest mode that the signal can propagate inside the waveguide. And what we can see here as well, this we can find the cutoff frequency for the dominant mode. So what we can see that if you put TEM is to 1 and is equal to 0, so you can see have that your C over 2A. Okay, so this is the dominant modes or the cutoff frequency for the dominant mode is actually is the lowest frequency that can be propagated in this particular waveguide. So usually we consider in terms of the dominant modes. The rest, the mode, if you put m is to n is to 0 and so on, you can find out that the values of your cutoff frequency is increasing and increasing and increasing. Okay, especially if you put TE 01, since your B is smaller, so you can see that you have a high frequency coming there. Okay, so this is very important for you to know what is the operative frequency for your horn that can be used. Okay, the horn antenna has a distinctive shape and is slightly unlike many other forms of antenna and is used at the microwave frequencies. So what we can see, you can find out that the horn antenna is being used for the microwave frequency. We are not using at the low frequency like UHF or VHF because what happened? The horn antenna is become big because due to the cutoff frequency of the waveguide. Okay, so the horn antenna can be considered to be a waveguide that has been widened out in the form of a horn. As a result, its find many applications. So usually what you can see here, the horn antenna usually you use is in terms of the feed. The very simple example here, you can see your astro, as you can see that your astro, as you know, your astro in front of your astro. The astro is just your parabolic. You just one reflector there on the top there. So there is a feed there. You can see in front of the astro, you have the feed there. So usually they use this what you call the horn antenna here. So that is the horn antenna that is being used in the at your parabolic antenna there. Shaped like horn, and this antenna form a smooth transitions between the waveguide and phase wave, also that the wave in the beam here. The horn antenna may be considered as an RF transformer or impedance to match between the waveguide feeder and the free space, which has impedance of this 377. By having a tapered or having a flare end to the waveguide, the horn antenna is formed and this enables the impedance. You can see that you have the advantages of this horn antenna. Wide bandwidth, the horn antenna possesses no resonant elements and therefore is able to operate worldwide. So if you know what is the cutoff frequency, let's say for example, you calculate the cutoff frequency, you got let's say 6 gigahertz. Okay, so what you can see that here in terms of the resonance, so you see you can have this is a cutoff. So it look like this waveguide it works as what we call the high pass filter. It means that above than 6 gigahertz, as you can see, this is the lowest frequency. Above this, you can see that the signal can propagate inside the waveguide. Okay, so that is the most important thing that the waveguide that you want to know. The most important thing is the dimensions of your waveguide here. So this one I took as a TE10. Okay, so we know that this is the lowest frequency that can be propagated inside the waveguide. Okay, so what we have here, so this is the, let's say if you calculate the cutoff frequency is 6, and then above than 6 gigahertz, the signal can propagate. Lower than that, the signal cannot propagate. So that's why you see that if you do the antenna at the microwave, it's okay. The size of the aperture is small. But if you talk about the VHF, UHF, the size of your antenna will become very, very big. So that's why horn antenna is not suitable to be used at low frequency, especially VHF or UHF band. Okay, so what we can see here, it's easy to interface to waveguide. By the very nature of the shape, they are very easy to interface to waveguide. So because as you can see that, I will show it to you later. And you can see also is a simple constructions, and the horn antenna consists simply of a flare horn. As a result, it's easy to construct. Okay, this one I show you all the standard waveguide. So if you go to the shop sometimes, if you want to buy the waveguide, so you cannot say that I want to use at this frequency wave. Usually there is a standard waveguide already that available in the market. You can go, let's say for example, if you want to buy L band, so this is the frequency that it can be used, S band, C band, S band, K band. So as you can see here, if we can take the example of WR90, so this is the X band. The X band frequency we use from 8 to 12 gigahertz. Okay, for the L band we use from 1 to 2. From the S band we use from 2 to 4 C. Okay, so this is my dimensions of the waveguide here. So the size is in inch. I think I want to show you in terms of millimeter. I think it's millimeter is much better because this one is from the US. So they give you in terms of the inch. Okay, so this one is the same thing. Let's say we took X is equal to this particular frequency, WR90 here. So this is a standard waveguide for the X band. Okay, so we know that the aperture of this waveguide has A and B here. A actually is 22.86 millimeter and B is equal to 10.16. Okay, can you calculate for me what is this cutoff frequency? Cutoff frequency for TE10, mean for the dominant modes. Okay, I want everybody should calculate what is the cutoff frequency for this particular waveguide. Okay, the cutoff frequency at the dominant modes here.
6.56 gigahertz.
Okay, correct. So I think you know how to get this. FC is the 6.56 gigahertz here. How you get FC actually is to C over 2A. A you know, C you know, so you get the FC here. Okay, correct. So what we can see here, this is the dominant modes. Dominant modes, as I mentioned to you before, is the lowest mode or the lowest mode that the signal can propagate. So in this case, the cutoff frequency, it means that the lowest mode, the lowest frequency that can be propagated inside this waveguide is roughly about 6.56. But as a standard waveguide that they use that they want to use this waveguide at 8.2 to 12.4 gigahertz. Okay, so it means that one is okay because actually you can use also this waveguide to transmit the frequency at 7 gigahertz, 7.5, and so on. But the standards that they we given for the X band, you see that we want to use at this particular range of frequency. So if you go to the shop, if you want to buy, okay, I would like to buy the waveguide or the horn antenna operate at X band. So they will give you the horn antenna here. Okay, the size of this aperture is about 22.86 multiplied by 10.16. Okay, as you can see that the same thing for KA and K band here. You see, so we can see that KA is 26.5 to 40. Okay, so this is WR28, WR40. This is the standard that the people use. Okay, WR28, WR42, WR62, and so on. In between there also there is also have. So there is another WR30 and so on. But this is the standards that usually the people use for this particular waveguide. Okay, so this is an example. You can see WR. Just now we use at WR90. Okay, WR90 is don't have here because so we start with the WR28. Okay, WR28 is here. KA band here. So this is the range of it, and then WR22. So you can see that WR3. So we see that the lower the value of this, see, you can see that WR34. So you can see that the frequency range is increasing because of the guided wavelength here. It's going to be smaller and smaller. So what you can see here at high frequency here, WR3, the aperture size here is the aperture size of this particular is become very, very small. You see, lambda G is about 2.214 here. The guided wavelength inside the waveguide here. 2.21 millimeter, you see, very small. So that's why if you want to use for the terahertz application, you can find out that the guided wavelength or the aperture size of the waveguide is very small. We don't have here. We don't have here in India. We don't have because of if you want to buy that particular waveguide, it is very, very expensive. So and then it makes from the gold as well. It makes from the gold coated with. Okay, so this is what you call the adapter. Okay, so what we have here. So you see the adapter is the transitions between the coaxial. So this is the cable. You connect to the cable. So this is N-type DSSMA. So this is the N-type adapter. And then you connect through your adapter here. So of course you need to have a cable here. And then the transitions, it will have a transition inside here. The cable, the like there's a coaxials. And then it goes to this waveguide. So this is your waveguide here. So most of the the antenna for the horns, so you need to have these transitions. Otherwise, if you want to fit here, it's very difficult. It's very so the easiest way is to use the just the SMA or N connector directly to your transitions to your waveguide here. Okay, we move to what do you understand by the horn example E plane. This is of the H plane. Okay, so this is the E plane. You see that this is from the aperture of your antenna itself. Okay, so this is the aperture here. At the E here is a vertical. This is the H plane. H plane is the horizontal. We look in terms of, we make the aperture at the B here. So this is what you call the H plane. And this is at the E plane. The aperture come from the A here. Okay. It will become like a horn. This is what you call the sectoral horn. So we can have in terms of E plane or H plane. So I hope that you understand. So if you have this, this, so the aperture here is your E plane. If you have the E plane, so if you combine both E plane and H plane here, so that's why you got the pyramidal. This type of antenna has flaring on both sides. So you can have, you see, you have the E plane here as well as the H plane here. Okay, so you see, so this is the E plane and then this is the H plane. So you can have both. So this become the pyramid. So the pyramidal actually is a combinations of both E plane and H plane of the rectangular. And we also have another types of horn antenna we call the conical. Conical is just the circular types of horn because I think you learn about the waveguide in rectangular as well as you learn the waveguide for the circular waveguide. So this one we need to use a circular waveguide. So how you want to solve this, you have to look in terms of the Bessel function and so on. It's the same thing. You find that you need to find what is the cutoff frequency from the circular waveguide here. Okay, so they use in terms of the dominant modes, T 1.85. So the value is 1.841, the T value here for the circular waveguide. If you learn about the circular waveguide before. Okay, what we can see here, so this is the structure of your E plane, H plane, and the view of your structure is okay. So you can see that if you look here, E plane view here, so you got this one. So what we have here, so you see, so you need to find out what is this is the horn here, and you have the value here. So what we can see that we define this one as the row E, row 1, okay, and with the angle of, so what we can see that row 1 here and P1 here, okay, so there will be slightly row 1 plus with the delta here. Okay, so this is the H-plane view. H-plane view will mean from the top here, sorry, from the top here. So you look from the top, so you can see that this is the A here. Okay, so the same thing, you have P2 here, row 2 and row H here. So, and then the P2 actually is a combination of row 2 plus your B here bit. Okay, so you want to find out this particular dimensions if you want to design the horn. Okay, so this is more detail as you can see that pyramidal horn. So we look, the first antenna that we want to design is a pyramidal horn antenna here. Pyramidal horn. As again, I showed you this is a E plane view, and this is a H plane view. So what the same thing, E plane view you find out at the B here, and this one is the at A here. Right. So what we can see, so this is the aperture size. Aperture size. So sometimes we use in terms of capital B, or sometimes this one is also capital A. So it's the same thing. So A is equal to A1, B is equal to B1. Sometimes I'm using this value. So if you can see, to differentiate it, because sometimes it's difficult to see A small capital C. Because, but in this case, we found out A and B actually is the dimension of the waveguide, as I mentioned to you before, A and B, and of course the the aperture size here, it depends on your pyramidal horn here. So that's why they put of B1 here or A1 here. So the most important thing, if you want to determine the gain of this antenna, it's much depend on this particular value, A1 here and B1 here. Okay, so you need to find out what is the psi E here as well. And then you need to find out PE here from the vertex here to the PE. So you can see, all right, so this is the PH here for the horizontal. And of course, you have a P2 here from here to here. Okay, so and then P2 actually is this one you plus with this. Okay, so I just want to show you, and then for the E plane, okay, a bit more bigger, the size of the horn here. So this is your P, the dimensions of your waveguide, and then this is your row E from this point to this, and for P1 from this point to the center of this, and then this is the aperture size, and from here we know that this is the PE here. So to physically realize a pyramidal horn antenna, so you need to find out this particular value. So to make sure that you can realize in terms of the pyramidal horn antenna here, if you want to realize in terms of pyramidal horn antenna here, so the value of your PE here should be equal to pH. So this is the conditions that you need to fulfill in order for you to make this antenna working as a pyramidal horn antenna. So how you want to find the PE here? PE here, as you can see, is equal to B1 minus B here, small here. Okay, so this is your B here, multiplied by rho E here. So this is from the theorem Pythagoras. If you try to derive it from the theorem Pythagoras, from theorem Pythagoras. Okay, so if you have like this, C, B, A here, so you can see that C squared is to A squared plus B squared. So the most important thing here, you want to find what is this particular value lah. So you see that, so B1 minus small b here, so this one you can find out in terms of B1 minus B here, all divided by 2, and so on. Yeah, so you can look in terms of this derivation from the Balanese. At the end, you want to find out what is the pH here and P. So you have to make sure that to realize as a pyramidal horn antenna, so you need to see that your this particular value is equal to the same. Okay. Okay, the same thing for the H plane. And just now we look in terms of the E plane. Okay, now in terms of the H plane also is the same thing. Okay, of course, if you look in terms of the picture, you can see that from the top here. So we know that this is a, and then you have also A1. The same things that you can find from the E plane. You can see that in terms of the equation, it's almost the same here. Okay. Okay, because first of all, of course, we need to find out the PE. PE is from here. This is pH lah because of the H plane. So this is a pH here. So at the end, you want to make sure that your PE is equal to your pH. Okay, so this one just to show you in terms of the quadratic phase approximations. Okay, in terms of this particular horn antenna that you can get. Okay, for examples here. So if you look in terms of this example here, you are given row 1, row 2, A1, B1, and so if you draw in terms of A1, so you want to make sure that this particular value is the same. Okay, so this is at any frequency here. So from here, you can find A1 actually is to 5.5 lambda is given. B1 is 2.75 lambda. And A is 0.5 lambda. B is 0.25 lambda. First of all, you try to calculate the rho E here. So the rho E is coming from this particular. Rho E actually is B1 minus B. Okay, and then you can find that rho 1 squared plus B1 squared, and then you calculate this value. You got this, and rho H, you got this value. And then you'll find out your PE here. As you can see that if you calculate these two values, PE and pH, based on this value that you obtain, you can find out the value is the same. So you can see that when this PE is to pH, so we found out that this antenna is working well for the pyramidal horn types of antenna. Okay, this one I just give you in terms of this. So maybe I can just give you in terms of the sentence. So maybe you want to design certain things from this particular horn antenna here. Okay, hold on. I just want to have a look from the books. Balanis gave you. This is a question actually, and then this is the solution that is being given to you. Okay, see the question is example here. Okay, so this is a question here. If a pyramidal horn has a dimension of rho 1 equal to rho 2 is to 6 lambda, A1 is equal to 12 lambda, B1 is equal to 6 lambda, and A is 0.5, B. So if you construct the pyramidal, so you can see that you have like this lah. Okay, so this is your horn. This is the A values. Okay, so this is your A1, Okay, so and then you need to find out what. So what you have here, you want to find out that what is the PE and PH here. So this is uh, for this one, for the AH plane. So this is your P2 here. Okay, so you want to find out this value of PH and PE. So PH should be equal to your PE here. So very important to construct the pyramidal horn antenna here. Okay, so if you calculate all this value, what you have here, okay, you find out your PE is equal to this value. And sorry, PE, rho E and rho H, you are getting this value. And PE and PH, you are getting these two value. You can see that this value is the same. So what we can see, if the value is the same, so you can construct your horn antenna easily. You can construct the horn antenna easily. To show about the directivity, so this is another important in the horn antenna. So there is a lot of different methods that you can find for your directivity. So the first one is the method one. What we can find out, the directivity of your horn antenna can be obtained from this. So this is a very long equations, some values. So and then at the end, you can see that you can simplify the. Okay, for the directivity of the horn antenna, it can be found from this particular equation, pi lambda square 32 multiply AB DE. So DE is the directivity for the E plane and DH is the directivity for the H plane. Okay, so what we can see that how you want to find DE here. So this is the DE and DH that you use, and then you need to put into these equations. Okay, so this is one of the methods that you can find the directivity of that your horn antenna. The second methods that you can find for the directivity of your horn antenna is by using these equations. 10 log this. So you can see the LE is the loss in dB to the phase errors. LH loss in dB due to the phase error in the H plane here. Okay, so you need to find all this, so you can find the directivity of this, where your T here is equal to this particular value. Okay, the number three methods, the third method that you can use is you calculate what is the A value here. The A value is the aperture size here. Using A and B, you can find GH and GES. So the gain for the H plane and the gain for the E plane. From this figure, if A less than 2B, then you use in terms of this equation, GH is to 32 over pi A, GE is 32 over pi B. Calculate DP using GH and GE here. So you can find that this equation is similar from the previous one. Okay, so we can see that we find out that you can use a three different equations. So this is to show that the loss figures for the E plane and the H plane here. Okay, in terms of LH and LS as we mentioned before to calculate it. Okay, right. So let's say if you are given this. Okay, so this was given in your question. I think it's the same thing as before. Now you want to find out what is the directivities for the three methods and physical realizability for the PE and PH as we mentioned before. Okay, so what you can see then, so this is the questions from this particular. Okay, so what we can see here is given here already. Okay, so actually the question is, okay, questions example here. Okay, pyramidal horn. So I want you to prove that you are getting this value. You calculate by and then after that you calculate using the three methods directivities that I showed to you just. So you need to find what is the row E here and row H. From there, you got your row 1 is given, row 2 is given. Okay, as you can see from these three methods, so the answer is very similar. As you can see here, the answer is very similar between method 1, method 2, and method 3 for this kind of a pyramidal horn antenna here. Okay, so you can use either these three methods in order for you to get the what we call the directivity of your horn antenna. The easiest, the simplest method, maybe you can use this method 3 so you can use because this is not really difficult because you can find directly straight throughout this. Okay, so first of all, you have to find out what is the A and B, and then from there you find GH, GE, and then you calculate, you put into these equations, and then you find out this is the equations that being getting from you. Compared to this one, you have to find what is the DE here based on this particular, but the equation is almost the same. Okay, so you need to find out all these values here. Okay, C, U, V, because this one you need to refer from the Balanese book to get all this value. Okay, so I think the easiest way you can find using this method 3 also no problem. You can use it. So first of all, you need to find what is the A, and then what is the B, and then from there you find GH, GE, and then you put into this equation, so you get this particular DP directivity is GE, GH over this particular equation. Okay, so this is an example of the standard X-band pyramidal horn antenna. So you can see that. Okay, so what you can see here, okay, so this is the dimensions that is being given to you. Where the value of C, the value of B, the value of A, okay, in terms of centimeter. And you also can calculate this particular antenna with a certain gain. So you can refer that here, the graph. At 9 gigahertz, the gain is around about 15, about 10 gigahertz, the gain about 16, 11, you have 17, and so on. You see, the gain increasing when you have in terms of the higher and higher frequency. Because of why? Because the aperture size will determine the gain value. Because the bigger the aperture size at the high frequency, so the gain will be increasing due to this particular horn. Okay, so this is a standard horn antenna. Okay, now we want to see in terms of how you want to design the antenna, because this one is more on design step is more towards, sometimes you need to have some trial and error as well. Okay, so if you want to design the horn antenna here, what you need to do as first step, find the value of T here. We satisfy the equation below. Okay, and then from there, once the correct T has been found, determine PE and PH using the equation and find the corresponding value of A1 and B1. Okay, because you need to find out A1 and B1 here. This is the aperture size that you are going to use for the specific gains that you want to find. And then from A1, B1, so you got this value, and then the value of P can be found by using the equation before. And then you can see that you can find last in terms of the gain here. Gain actually is to, if you assume as the efficiency is only 50%, at the end you find out the value of your gain actually is half of your pi lambda square A1 multiplied by B1. So this is the aperture. A1, B1 is basically is the aperture size of your horn antenna. Because usually since we know the efficiency is not 1, okay, so we have the efficiency is roughly the half of 50%. So we can see that the gain actually is a 50% of 4 pi lambda square A1 multiplied by B1. So this is the simplest equation that you can use to find the gain of the horn antenna based on the aperture cycle. Okay, you see that? You have G0 and then A1 is to this and this. So this is the equation that I discussed before, and then from there you can calculate. Okay, for example here, so we can have a look. The example for the horn antenna. Okay, you were given the X band. X band, as you know that, the operating frequency is from 8.2 to 12.4. Okay, and then because the question is, we want to determine, the question is, okay, 8.2 to 12.4 gigahertz pyramidal horn antenna, so that its gain above isoscope as F is to 11 gigahertz, horn and gain 22.6 dB. The horn is flanked by WR90 rectangular, so this is standard waveguide with the A is equal to this. How you want to do this? First of all, you need to find what is the gain here in the ratio value, absolute value. So roughly is about 181.97, as I mentioned. And F is equal to 11 gigahertz. The lambda actually is equal to 2.723. So you need to calculate it by yourself and see whether you are getting the correct answer or not. Okay, so this is the waveguide dimension. Okay, so we change it in terms of lambda value. So of course, if you change to lambda value, you have to divide with the lambda here. So you will get the A actually is 0.3725 lambda. B, sorry, and A is equal to 0.8382 lambda. Okay, so we change already. So we have dimensions here, A and B here. So A actually is equal to 0.8382 lambda, and B 0.3725 lambda. Okay, so you have these two particular frequency, these two particular dimensions here. Okay, for the waveguide. Okay, everybody got it? Okay, yeah, can okay, next, next, this is the things that you sometimes you need to find out here, the chi values, the chi values here. Okay, so if you put into this equation of the chi that we have for the design specification before, you need to have a trial and error. So chi is to G naught, this is particular. And then what you have here, you got this value. Okay, if you look 12.56 for all these equations, if you put here, actually it's not really satisfied with the answer that you are getting here. Okay, since it's not really satisfied, so you need to do some approximations value until you obtain these two particular value is the same. So it will takes you time lah, this one, because this is more the design, the design here is more accurate if you use this concept. So, and then after do some iterations, you found out that the chi value is roughly about 11.1157. Okay, so it's instead of this one, because if you put into this equation here, so basically you are not getting, the value is not all the same. So what you can do after a few tries, a more accurate value, so you need to find out, and then you find out your chi here is equal to 11.1157. And then after that, what you need to do, you need to find out what is the rho E here. Okay, rho E is given as these equations. Okay, rho E and rho H here in terms of these two equations here. Okay, so and then you know that the value of chi here and lambda. So, and then you find out this is equal to this particular value. And rho h here is equal from these equations. So rho h, okay, rho h you got from these equations here. Okay, so this is rho h. Okay, you put into it, so you got this value. So now you know that you have rho e and rho h. After that, you can get the value of your A1 and B1 from these three equations. Since you know that rho 2 and rho h is almost the same here. So you just put into this equation, you got the value of 6.002 lambda, and B1 actually is equal to 4.715 lambda. Okay? Right. And then after that, you put back into this equation, because you know that you need to find PE should be equal to PH here. So this is a very important criteria that you need to find out, so that you will get the correct pyramidal horn types of antenna. Okay, so once you calculate, you got these two values is the same. So from here we know that if your PE and PH is the same, so we can make this thing in terms of your pyramidal horn. Using method 1, method 2, and method 3, you can find out the gain is almost very similar to each other. Only 0.03 or 0 to 3 but lambda only difference from one another. Okay, so this is the three methods that you use to design the horn antenna. Okay, so now after that, as a summary here, what we can see as a summary, to physically realize a pyramidal horn, okay, the value of your PE must be equal to PH. So this is the most important, where B1 is the aperture size, B is the aperture diameter of the parameter of the waveguide, and rho E is the value from this particular value for the E plane, and all this value you can find. And then once you calculate this value, you can see that you find out your PE is equal to your PH. And then how you want to determine the directivity? The directivity from this method 1 can be used in terms of this. DE 64 A rho 1 over 4 pi lambda, and so this is with the value. And then for the directivity of method 2, you find out this. And the method 3 you can find from this as well. So where your LE is lost in dB due to phase error, so this is the value that you can obtain from the graph. And then this is the directivity obtained from the equations that you have from here. And this is the directivity that you can get it from your equations here, GE and GH here. And then at the end, you find out this one is very similar with this one, same, almost. Okay, so as a summary for the horn antenna design here, what you need to do, gain, you need to find what is the gain, G naught, gain of the antenna. And also you find out your A1, actually the aperture size, okay, for this one. So this is your A1 here, is 3 lambda rho 2. So we assume as rho 2 is to rho h here, same here. So you have rho 2 is equal to rho h, rho 1 is equal to rho e, and you have to make sure that your PE is equal to PH, okay, for the pyramidal. Okay, so you find out this particular value, you know, all this one you know already, this one you know, this one you know. So you want to realize this, you have to make sure that your PE actually is equal to your PH. Okay, so as to how we want to summarize the horn antenna here. So first of all, you need to find, if given, a gain is given. So you find out trial, we can find chi value here. If the chi, once you put into this equation and you find out the chi is not really So you need to do some iterations to get the best value for t. And then from there, you find your rho e here and rho h here. Rho e is t multiplied by lambda. A1 from here, you got it. B1, and you have to make sure that your PE is equal to rho h here. Okay, right. Is there any questions to ask? Allah, tak boleh. Okay, why not we try